are in Statistical Rethinking, second edition, and we are in chapter 12. And we're in the easy questions, question 12E3. Okay, so here's the question right here. So when count data are zero inflated, using a model that ignores zero inflation will tend to induce which kind of inferential error? Okay, so so hopefully you've read the chapter, but zero inflation is a distribution wherein there are more than more than the expected number of zeros, right? So I think that the example that's given in the book here is you have monks that are producing handwritten manuscripts or books, I guess, and you're logging how many books they produce each day, and sometimes they produce one or two, and sometimes they produce zero. But they can produce zero for more than one reason, right? They either take the day off, or just because it takes a long time to write these books, just none get completed. So there's more than one mechanism by which zeros are being produced in that situation. And so there tends to be more zeros, hence zero-inflated, in that type of a process. Okay, and so we're asked, what kind of inferential error is caused by using a non-zero inflated model to model zero inflated data. Okay, so here's my answer. We're actually going to demonstrate it. Okay, so there's probably a few ways to answer this. So of course the first one is that the number that if you're not modeling your data as zero inflated, you are almost certainly going to underestimate the number of zeros in your data, and then also thereby overestimate the number of non-zeros in your data, right? Because if you're predicting less zeros, you're going to predict that non-zero values are more likely than they actually are. Okay. Now this actually has knock-on effects, and like I said, we're going to demonstrate this here in a second. But because you are not predicting as many zeros, you're going to tend to overestimate the actual mean value of your data, right? Because you're ignoring a bunch of zeros. You're assuming that some of the zeros are not zeros, and therefore you are artificially inflating your mean, your estimate of the mean. But something else that may be a little bit, well, kind of something that you'd have to think a little bit more about is that you're also going to underestimate the variance. And I think that this is the thing that the demonstration will be most valuable for. But when you have these multiple processes taking place, you are increasing the variability in your data, right? Because for the monk example, you have more than one process producing, well, just producing whatever the outcome happens to be. So not only is there variance associated with the process, there is also variance associated with which process is, being employed. Okay, so overall then, the effect is you become more confident about an incorrect estimate, right? You are misestimating the mean and you are underestimating the variance. Therefore, you are more confident about an incorrect estimate if you are ignoring the zero inflation. Okay, so so let's look at that. So here's some code here. So just let's walk through it. So we have one variable, and it's a Poisson random variable that has a mean value and therefore a variance of 3. Lambda equals 3. So in Poisson models, lambda is both the mean and the variance. Okay, and then I have another variable x2, and then we're going to fill out x2 right here. Okay, so so x2, I'm going to first I'm going to generate a random variable, a Bernoulli random variable, so binomial random variable, that I'm just going to generate one value, and it has a 10% chance of being a 1 and a 90% chance of being a 0. When that random variable is 0, then the value of x2 is also just a Poisson random variable with lambda 3. Okay, same as x1. But 10% of the time, it's a 0, right? So I've zero inflated x2. Okay, that's all that this for loop is doing. And then we'll see the mean and the variance, and then we'll also look at the histograms overplotted one another. Okay, so here we have it. So let's just look at the values here first. So So this value is the mean of x1, the one that is not zero inflated, and it says that the mean is about 2.974 or about 3, right, which is expected, and the variance is about 3, right, because again in a Poisson random variable, these two are the same, right? They should be the same. Okay. Now let's look at x2, which again was this mixture model, this zero inflated model. Now its actual mean is less, it's 2.6, and its actual variance is greater, okay, which is what we talked about in the beginning. So in other words, if I were to have used a Poisson model to model my zero inflated data, again, I would have underestimated the mean, okay, right? I would have guessed 2.9, but it's actually 2.6 or something like that, okay? And I would have been more confident. I should only be confident to the level of variance of 3.5, but I would have been confident to the level of 2.9, right? And so you can see how these things play out here. So the red is x2, is the zero inflated data, and so you see many more zeros here, okay? And so by virtue of having many more zeros compared to the actual Poisson distribution, right, it has more zeros, but then every other bin here, it has less, it's lower in every other bin, okay, compared to just the Poisson random variable, okay. And then also notice how the mean is shifted, okay. And it's a little bit hard to get a sense of the variance here. If you run this a few times, you'll probably, if you run this several times, you'll tend to get this red tail out here. In other words, there's more extreme values because again, it's more variable. Anyway, okay, so I guess that's all that we wanted to show here.